Hidden beneath this thin blue horizon is a problem that sounds impossible, making ocean water drinkable on an industrial scale. Here, salt concentrations are around 35,000 milligrams per liter, and dissolved ions are separated by channels smaller than a single atom. To turn that vast corrosive soup into freshwater, engineers push physics to the limit. We compress seawater to pressures of 800 to 1,200 pounds per square inch, and force it through membranes with pores measured in fractions of a nanometer. This is a fight against diffusion, corrosion, biofouling, and sheer scale. A single coastal plant can treat hundreds of thousands to millions of gallons per day, and every inch of pipe, pump, and membrane must withstand brutal chemistry and relentless pressure. In this film, we follow the entire transformation, from raw ocean intake to a drinking water faucet. We will trace the materials, stainless steel, concrete, polymer films, and the microscopic chemistry, like interfacial polymerization, that creates a barrier thinner than a human hair. Every step balances cost, energy, and the environment. This is industrial alchemy, turning saltwater into safe, reliable freshwater with numbers that force you to look closer. Before a drop is purified, the plant must harvest seawater without choking on sand, algae, or fish. Intake systems begin with engineered screens and coarse sand filters that remove particles larger than a quarter inch. Offshore intakes sit tens to hundreds of meters from shore, or the plant uses shore-based submerged wells to reduce biological intake. The seawater stream is metal, concrete, and pumps, mostly duplex stainless steel and carbon steel lined with epoxy. The membranes themselves come from petrochemicals, polysulfone supports, and a polyamide active layer produced by interfacial polymerization using M-phenylene diamine and trimesul chloride. The active film is measured in 100 to 200 nanometers thick, and its pores are smaller than 1 nanometer. Energy systems rely on electric motors, typically variable frequency drives rated in hundreds to thousands of horsepower, and sometimes on combined cycle plants or renewables. Chemicals for pretreatment include coagulants, antiscalants, and chlorine or biocides, dosing measured in parts per million. Every raw material carries a specification: tensile strength, corrosion allowance, chemical resistance. Getting these parts right is a material science problem as much as a hydraulics problem. The ocean is plentiful. The challenge is harvesting a clean, stable feed that will not destroy the heart of the plant. You cannot run a high-pressure reverse osmosis train on raw seawater. Pre-treatment protects the membranes and recovers efficiency. Step 1 is coarse screening to remove debris larger than a quarter inch. Step 2 is media filtration, sand or multimedia beds that trap suspended solids to about 10 to 50 micrometers. Many modern plants use ultrafiltration modules next. Ultrafiltration removes particles down to 10 to 100 nanometers, bacteria, and some viruses, producing a steady, low-turbidity feed. Antiscalant chemicals are dosed continuously to prevent sparking crystalline deposits as concentration rises. Operators monitor turbidity, silt density index, and free chlorine. These controls operate on second-by-second feedback loops. Temperature matters. Warmer water increases permeability, but also accelerates biofouling and chemical degradation. Pumps and valves in pretreatment are often lined with fluoropolymers or built from duplex stainless steel for corrosion resistance. Proper pretreatment cuts membrane cleanings from weeks to years and lowers energy per unit of permeate. In short, pretreatment is where subtle chemistry meets hydraulics. If it fails, the rest of the plant grinds to a halt, so engineers design redundancy, automatic backwash cycles, and real-time sensors to keep the feed perfectly conditioned. At the heart of desalination are thin-film composite reverse osmosis membranes. These start as rolls of porous polysulfone support. In a controlled line, the substrate is flooded with an aqueous solution containing M-phenylene diamine, then contacted with an organic phase containing trimesul chloride. At this liquid interface, a polyamide film forms in seconds. That active layer is usually 100 to 200 nanometers thick, thinner than a hair by a factor of 1,000, yet it rejects salts with pores on the order of 1/2 nanometer. The membrane is then cured, washed, and rolled. Tension, coating speed, and reactant concentrations are controlled to within single-digit percentages to maintain consistent rejection and permeability. After fabrication, modules are wound into pressure vessels on stainless steel mandrels, typically in 4-inch to 8-inch diameter elements, stacked to form trains. Quality checks measure salt rejection, permeability, and bubble point. Packaging considers hydraulics. Feed spacers create defined flow channels to minimize pressure drop and biofilm formation. This is precision chemistry turned into mechanical form, a polymer skin so thin that microscopic defects will determine plant performance. Manufacturing scale and material purity matter. One bad roll can cost millions in lost production. To desalinate seawater, you must overcome osmotic pressure. That requires heavy-duty hydraulics. High-pressure pumps in seawater reverse osmosis systems are positive displacement or centrifugal units with stainless steel casings, ceramic plungers, and seals rated for sustained duty at 800 to 1200 pounds per square inch. Piping and pressure vessels are specified with corrosion allowance and safety factors. Pressure vessels are often fiberglass reinforced plastic or carbon steel with epoxy lining. Engineers design feed trains to maintain steady flow and minimize transients that can shock membranes. Valves use double mechanical seals and shaft purges to keep seawater from attacking bearings. Instrumentation measures flow rate, differential pressure across each element, and permeate conductivity in real time. Thermal considerations matter. Friction and pumps raise temperature slightly, which affects viscosity and membrane permeability. Maintenance routines include seal replacement intervals measured in thousands of operating hours and vibration monitoring to detect misalignment before catastrophic failure. Every flange, gasket, and fastener is specified to resist chloride-induced stress corrosion cracking. In high-pressure systems, attention to materials, tolerances, and hydraulics is what keeps the plant running day after day. Energy is the dominant cost of seawater desalination. A typical seawater reverse osmosis plant consumes 3 to 4 kilowatt-hours per cubic meter of product without recovery. The breakthrough was energy recovery devices that capture pressure energy from the outgoing brine. Rotary pressure exchangers can transfer up to 96% of the hydraulic energy from concentrate to incoming feed. In practice, a pressure exchanger is a precision-engineered rotor that spins at thousands of revolutions per minute, matching pressure pockets to transfer energy with minimal mixing. Isobaric chambers, turbines, and piston-type exchangers are alternatives. Coupling these devices with variable frequency drives and optimized staging reduces net energy to around 1.5 to 2 kilowatt-hours per cubic meter in modern plants. Engineers design for cavitation risk, erosion from high salinity flow, and seal longevity. Mounting and alignment tolerances are tight. Microns matter at high rotational speed. Energy recovery is both mechanical engineering and fluid physics, and it turns desalination from an energy extravagance into a scalable water solution. Desalination plants are built from modular building blocks. Engineers fabricate skids, welded frames containing pre-assembled pumps, valves, membranes, and control panels. Modules speed construction and allow factory testing before arrival on site. Each skid has integrated piping with union fittings, pressure relief valves, and a control cabinet with a programmable logic controller that manages startup sequences, backwash cycles, and emergency shutdowns. Sensors measure conductivity, pH, pressure, and flow at high cadence, often 10 to 100 samples per second for critical points. Control algorithms use feed-forward loops to anticipate salinity changes and closed-loop PID control for pressure and dosing. Wiring harnesses are sealed to NEMA or IP ratings for marine environments. Engineers tune membrane trains in parallel and series to balance recovery and flux. On site, cranes lift skids into place and technicians hook up seawater intake, power, and discharge manifolds. Factory acceptance tests include hydrostatic pressure testing to design pressure plus safety margin and loop checks for every instrument. Modular design reduces on-site time and concentrates craftsmanship into factory environments where tolerances are easier to hold. Before a plant operates for customers, it faces torture tests. Operators perform hydraulic shock tests, cycling pressure from zero to design pressure rapidly to check for leaks and fatigue. Membranes are salt challenged with controlled feed to confirm salt rejection and permeability targets, and foulant surrogates simulate algal blooms. Chemical compatibility tests expose seals and gaskets to prolonged chlorine, antiscalants, and biocides. Electrical systems undergo surge and ground fault testing to ensure safety in coastal, lightning-prone zones. The plant runs endurance trials for thousands of hours to observe creep, corrosion, and biofilm development. Water quality laboratories measure permeate conductivity, turbidity, and microbiological counts. Typical targets for potable-grade permeate are below 500 milligrams per meter total dissolved solids and turbidity under 1 nephelometric turbidity unit. Performance data are logged at high frequency and analyzed for trends. A small rise in differential pressure predicts fouling weeks in advance. These tests reduce risk and define maintenance intervals. In this phase, statistics and engineering meet. Mean time between failures is verified, spare parts lists are finalized, and operational manuals are written from real-world data. Desalination produces concentrated brine that must be handled responsibly. If inlet seawater is about 35,000 milligrams per liter, concentrate can climb to 40,000 to 70,000 milligrams per liter depending on recovery. Engineers dilute and disperse brine using multi-port diffusers to reduce salinity and temperature plumes near the seabed. Diffuser design relies on hydraulics. Momentum jets mix brine with ambient seawater to achieve regulatory compliance within meters of the outfall. Alternative solutions include deep well injection, evaporation ponds, or zero liquid discharge systems that recover salts but at high energy cost. Environmental modeling predicts impacts on benthic life, and monitoring arrays measure dissolved oxygen, salinity, and heavy metals continuously. Material selection for outfall structures emphasizes corrosion resistance and biofouling mitigation because concentrated brine accelerates deterioration. Engineers also design for chemical management. Antiscalants and coagulants must be dosed to minimize ecological toxicity. Brine handling is not an afterthought. It is an integrated design challenge combining fluid mechanics, marine science, and regulatory policy to keep the plant sustainable. Commissioning turns engineered systems into reliable service. Startup sequences begin with slow feed increases, membrane flushing, and staged pressurization to design conditions. Control systems ramp energy recovery units and high-pressure pumps to synchronize torques and pressures, avoiding transient spikes. Operators monitor permeate conductivity, flow, and differential pressure, adjusting anti-scalant dosing and backwash schedules. Routine maintenance includes membrane clean-in-place cycles that use acid and alkaline cleans at controlled temperatures to remove scaling and organics. These cycles are scheduled by condition monitoring, not by calendar. Life cycle planning considers membrane replacement intervals of 2 to 5 years, pump overhaul intervals measured in tens of thousands of hours, and spare parts provisioning. Plants optimize for cost per cubic meter of water, balancing energy, chemicals, and capital amortization. In the field, desalination becomes a continuous engineering problem. Operators respond to seasonal seawater changes, algal events, and storm-driven sediment loads. The result is resilient, predictable water delivery, taps flowing with water that once was ocean, made safe by chemistry, material science, and relentless engineering precision. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this tech archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.